I hope that, let us see if it's working. Okay, seems to be working. There is a delay, but that's all right. Now we are going to talk about the second aspect of the exercise that I had given you, which was about apparent and absolute magnitude. Now, I told you how distance plays an important role, obviously, because if you hold a bulb right next to your face, it's going to be a lot brighter than the moon, but it doesn't mean that the bulb is brighter than the moon, it just means it's closer to you. So there is the apparent magnitude and the absolute magnitude. So you know that the sun is like the brightest object in the sky, and the brightest star in the sky is Sirius. But um, how do we know if the sun is, more luminous than Sirius? We from our perspective, it looks like the sun is apparently brighter, but what if they were at the same distance from us, both sun and Sirius? Would we have we would then know which one is actually more luminous. And it so happens that Sirius is more luminous than the sun. I hope the audio is all right. If it's not, then I will have to delete the whole thing. I had problems with the audio with the normal screen capturing software earlier. Okay. I came to Stellarium to show you that you have your here absolute magnitude and you have magnitude, which is apparent magnitude. Here it says 0.07 and the absolute magnitude is 0.57. So that means that the absolute magnitude is, well, the star must be closer than 10 parsecs. 10 parsecs, I think, is the distance at which that's the distance we consider for absolute magnitude. I mean, what is absolute magnitude really? What we say is that if this star were at a fixed distance of 10 parsecs, yes, it is 10 parsecs. I had confirmed it when I wrote this. So they're all at different distances, right? So what if we put them all at the same distance, and then we can surely say that the brightest star is actually bigger or more luminous, I mean bigger or hotter, whatever. So yeah, luminosity, I'll talk about it later. It's a function of many things like temperature and surface area. Well, mostly the two things. Okay, why am I here right now? Um, there was a meteor simulation here. It's like seeing a meteor in real life. Altair, Altair. I don't know. I just make up accents. The magnitude is 0.75 and the absolute magnitude is 2.20. And I think they must have given this distance, and that's 16.73 light years, and that's less than 10 parsecs. And I hope you know how I can predict which star is farther. And I mean, it's easy, right? Because if a star, let us think about now these stars which are, brighter in our sky, that's because like many of them are close to us. um, Alpha Centauri, which we used to think was the closest star to us, well, now we know it's Proxima Centauri, the small random star no one cares about. But okay, Proxima Centauri is bright because it's close. Capella is, it's like almost zero, but the okay, no, absolute magnitude is actually brighter, so it must be farther away. Yeah, it is farther than 10 parsecs. It's 42 light years away, so it must be a big and bright star. 10 parsecs is about, I don't know, 26 light years. What is um, 1 parsec in light year? 3, okay, sorry, so 32.6 light years. Okay, now let us go to our questions. If I hope I have made the whole thing clear. Okay, no, we can actually, I'll just show you. The sun. What are the other names for the sun? It should be Sol or something, right? Okay, the sun's magnitude is minus 26.73, And why don't you calculate how much? Well, I have actually given it here. Assume that the sun's apparent brightness is 10 to the 10 times that of Vega. But you can calculate like from I1 again, but let me not give you more homework right now. Okay, so you can see that the magnitude is minus 26.73 and absolute magnitude is 4.83. So, uh, if there was a planet which is 10 parsecs away from us, then the sun would look like, no, not even this. No, not the nebula, not 3.4. That's too dim, too dim. Huh, about this much. So if we are sitting on a planet which is 10 parsecs away or 32 light years away from us, then this is what the sun would look like from that planet or wherever. I mean, you don't have to be on a planet, you could be just floating in space. But yeah, the sun would look so tiny and small. It is like an average star. Uh, it's not very special, we are just very close to it. Yeah, we should love it. It deserves all the love. Why not? I mean, it's not like it's, making our lives difficult. It's the reason why we exist. It's constantly outputting energy, and that's why we are, moving and walking around and converting entropy and stuff. So, okay, coming to the question. I think you can handle this question. Um, Assume that the sun's apparent brightness is a billion. Billion is 10 to the power 9, so that's like 10 million. 10 billion times that of Vega. Vega's apparent by magnitude is 0. Use the formula created in question 1D to, did you create it in question 1D or question 1C? To calculate the apparent magnitude of the sun. Don't be shocked. So, well, we just saw that it's gonna be minus 26 point something something. I mean, that's the real thing, and this is like my number, the 10 to the power 10 thing, but let me just do it. 10 to the power 10, right? So we have 10 to the power 10. That's the difference of magnitudes. That's the intensity difference between, well, we don't know what this is. This is the x is the magnitude of the sun. That's actually, I want to have a discussion about it. Is the sun a proper noun or a common noun? Anyway, and we know that it's not the magnitude, it's the ix by I Vega. Well, no, we can't use this here because we have used it for x. So I 0.0. Now, can you figure out the x? We know that the step size is 100 raised to 1 by 5. If you are going in towards the negative direction, so this, otherwise it would be 1 by 100 raised to 1 by 5. If you are, so this is the step size. If you are, this is this is equal to um, mag intensity of, let us say, 3 by intensity of 2, and this is equal to intensity of 2 divided by intensity of 3. Okay. So this must be, let me just undo this. Now we want to find out how many of these give rise to an entire, like, okay, so what is 10 raised to 10? That's 100 raised to 5. Okay. And what is the number we need to raise this number with? Let me raise it, because this is our geometric step size, right? 100 is to 1 by 5. So we need to raise it like, ah, I am not making this clear. I'm perfectly aware of that. So it's like 2 a.m. I can't sleep, and that's why I'm doing this. So basically, we have our number line which is an exponential or logarithmic number line, and we have 0 here. Ah, it's so difficult. Okay, I didn't want green, that's what. We have 0 here, we have 1 here, we have 2 here, and we have -1 here, -2 here, -3 here, and so on. And we know that this difference accounts to like 2.5, whatever, what it's actually little. 2.5 is unnecessary. It's 100 raised to 1 by 5. That's how many times -1 bright, like a magnitude star is brighter than a magnitude 0 star. And then if you go to minus, here it's -4 and -5, so that would mean that you add these all up, as in you multiply these all, and that gets added in the exponent, this number. So that's 1 by 5 plus 1 by 5 plus 1 by 5 plus 1 by 5 plus 1 by 5, not 5. That's 100 raised to 1 by 5 raised to 5. That's just 100 raised to 1. So a -5 star is 100 times brighter than a 0 star, a magnitude 0 star. And we have been told that it's actually 10 to the power 10, or 10 to the power 10 is equal to 100 to the power 5, because you have, I mean, you can do it, you have passed school. And then 100 comes with 5, and then we need to go 5 more, and to go 5 more in like it's basically 25. I mean, you must have figured it out by now. Why? Because if you need to reach 100 raised to 5, and if you're then you'll have to raise 100 raised to 1 by 5 to a power of 25. Then this becomes 100 raised to 5. So that means you have to go 25 steps in this direction. So that's the answer to question 2. So question 2 answer is, it feels so weird solving the questions that I made, and actually I just made them and I didn't solve them myself. That's a bad thing. But next time I'm getting them checked with my friends, so I won't give you incorrect questions. But as it happens, oh, this is -25 by the way, because we're going in that direction. So the sun's apparent magnitude would be -25 if it's 0.04 Vega. You need a reference, right? Anyway, let us go to the next question. You live on a top of a hill in a village. So here now we will be talking about distance, because it is important. And I'll test how well you have understood this, or how well I have been able to teach when we meet, because I don't know if I'm making things clear. And please tell me, you can PM me on Telegram if you're not understanding, because it just means that I need to be more, and you can also tell me if I'm going too slow for you. We already discussed that we have two kinds of people in class. We can probably, make different tutorials. Okay, anyway, you live on the top of a hill in a village. One night, electricity suddenly disappears, plunging the entire town in darkness. And you go out of your house, you notice that there are two bulbs in the village that are still burning. You live in a very remote Indian village where people don't use like batteries and generators, but then there are these two bulbs that your friends have, and there is no other source of light. Let us say that all the kandils and diyas, they're all gone for some reason. It doesn't matter. I mean, even if they are, you can still identify these bulbs. That's what's important. But the noise of the others would just make it a bit hard. So there are these two bulbs, and they are like, they give out equal power, right? And they are the same bulb basically, and they are both equally charged, because with bulbs it's like when the battery starts going low, they start becoming a little bit dimmer, but nothing like that is happening. They're outputting the same amount of power. One bulb appears to you from wherever you are to be brighter, and the other bulb appears to you, I mean, you look, they're like far away, they're in the village, and you live on a mountain or hill or something, and the village is down there, and you see one bulb, like very tiny dot, and one another dot, and you can see that one is brighter and one is dimmer, maybe with your eyes or maybe with your telescope. So that must mean that the brighter one is closer, right? Because there is no other explanation for it, because they have the same luminosity. Now you want to find out, okay, so you happen to have a telescope and a photoelectric detector with you. That's just like fancy words. You don't need to, worry about how does the photoelectric work. Just don't care about it. You know that the closer bulb belongs to Charlie. That I watched Kamine that day. That's why. It belongs to Charlie, who lives exactly a kilometer from your house, like bird's path. And the farther bulb belongs to Guddu, but you do not know how far he lives. You point your telescope to Charlie's house and find that the bulb from his house creates a voltage of 64 milliwatt volts in your detector's chip. And now you point it towards Guddu's house, and this time it shows it's 36 millivolts. And how far do you think Guddu lives from you? How far do you think the Guddu lives from you? And the hint is 4 pi r square. That's okay. So let me just explain this to you, and that's because I don't know if I made it simple enough to understand for everybody. As in, I don't know if you are like, this is JE kind of question, you should be able to handle it. So you have one bulb here. No, wait, let me try to always make a diagram, it helps. So you are here with your telescope, and you see that there is like one bulb is here. Oh, you can't see this, no? Let me try orange. One bulb is here and one bulb is here. And this distance is 1 kilometer, and this distance you do not know. So this is 1 km. And what is this is the question. What do you know as is that they both give out the same flux, okay? And which is like, I don't know, let's call it I and I, because they're both the same flux. But then you in your detector chip, like you have some camera here, where you see that one bulb is like this big and the other bulb is like this big, and that's just what it means. And so the millivolt, like the voltage caused by this bulb, what happens is that these photons go inside the chip and then they excite electrons, and the brighter the source is, more electrons get excited, and so on. But all you need to know is that the difference is like 64 by 36. And that's and why. So if you see perfect squares like this, you know that there is something has to do with the square, like it feels like you need to take a root of this. And why is that? Because if a spherical source is emitting light in all directions, like a sphere, actually, like it expands throughout space in a spherical manner, then the energy, like the energy that it's outputting per unit time, is constant. But when it expands, you have to, if you want to capture all of it. Now let us say that I can't find a sphere. I have the earth, the globe somewhere. Oh, okay. So this is, let us say, a star, and it's giving out energy constantly, or a spherical bulb, which is like a metaphor for a star. Then I don't know if you can see this. I hope you can. Now if I want to capture all of the energy coming out of this star, I have to like hold it like this, so I capture it. But if I'm just putting my hands here, then I'm getting partially, like I'm not getting all of the energy, right? Because, well, it's going out in that direction and that direction and that direction. So if you want to keep capturing the entire energy of a star, then you have to put a big sphere around it and capture all of it, so that none of it escapes. But you are not doing that in this example, because your telescope detector, the aperture size is limited, so you're only capturing like limited amount of light. But how does it like, what's the relation between distance and um, intensity of light? And that's when I say 4 pi r square, that's because that's the surface area of this sphere. So that means that as the sphere increases, the intensity goes by down by r square. If it was like a well, in what case would it be linear? That's a question I would like. That's maybe you think about it. If it's a cylinder, like if it's a laser and it's not diverging, then it's gonna be the same intensity at any distance. If it's diverging linearly, like there's an angle, then what would it be? But don't, I will think about it and tell you later. But as it so happens that it goes down by r square, like with distance it goes down by r square. So if you are from a star at a distance of d from a star, this is you, and then your friend is at a distance of 2d, as in d plus d, then if you see that if you measure this to be I, your friend will measure it to be, or let us say that here, like right next to the star is I, then for you, no, for you if it's I, for your friend it would be I by 2, no, it would be I by 4 for your friend, because it goes down by r square. And we need to use the same logic here, that the ratio is what, 36 by 64, that's millivolts. So this is the amount of photons that has fallen, like just take it so, on the detector, and these are the amount of photons that have fallen on the detector from the farther lamp, and this is from the closer lamp, and they both have the same luminosity. Then that must mean that this is the ratio of the distances. But it's the inverse, okay? So because now here if you take the so it would be r square of Guddu was farther, right? Guddu, and r square Charlie. You understood why it's inverse. I mean, obviously, if it's the farther bulb is dimmer, so yeah. And then obviously it would be 8 by 6 equals r by r Guddu by r Charlie, right? So, and we know that r Charlie is like 1 kilometer. So r Guddu is 8 by 6, which is what, 1.33333. Okay, right? 8 by 6 is that much. I think so. It's just, I mean, so I do maths in Marathi in my head, and then it feels weird to do it in front of you guys. I can't believe I'm Googling 8 by 6. Come on, it's why is it a quick find here? Go away. Yes, I was right. Huh. 1.3 kilometers. 1.33 or 1.34 kilometers. You know, if we use the base 12, then we wouldn't have this problem. This would just be 1.4, but the world is not ready for base 12 just because we don't have 6 fingers on each hand. Okay. And you can see that just in this 300 meters, what has happened? It's such a big drastic difference, almost half the flux in just this much. And that's the thing about R square law. It's insane. Okay, next question. Is it still live streaming? Yeah, it is. Okay. You live in a top of the same thing. Now you are not given the distance. What you are given? Okay, so I'll just read the question. Except one bulb which belongs to Sweetie. You remember that the bulb gives 60-watt output, and you grab your telescope and your photoelectric detector and point it towards the bulb, and you have a device that tells you the received wattage on the telescope mirror, and it reads 0.00006 watts. Your telescope mirror has a diameter of 50 centimeter. Now, in the last question, I had not given you the diameter, and we could still do it because we had two bulbs and we knew how far one the bulb was. And now we do not know how far one bulb is. We only know how far, we don't know, we know how bright it, like how luminous it is, absolute, like how much power it's outputting, and we know how much of the power we are capturing. And there are two things here. What determines how much power would you capture? One thing is, if you put a big detector all around the bulb, you would capture all of the power, but you're not doing that. You are only like small mirror, you're only taking the tiny fraction of that power. So from these two informations, these two information one is that the bulb is 60 watts, and the other is that you are receiving 0.0006 watts. I don't know, and three information. The third is the diameter is 50 centimeter, assume it to be circular. How far are you from Sweetie's bulb? Now I think you should be able to do it on your own. I don't need to solve it for you. So pause the video and try it for a while. Like, pause now. Did you pause? Okay, now I'll just solve it. I hope that you were able to solve it. So this is like the sphere and like the cross section of the sphere, and your telescope is like this much of it. Now let us assume that you are some r or d distance away from that bulb, and at a d distance, the sphere would extend to pi 4 pi d square, like total area of the that sphere of radiation, and out of which you are capturing. Actually, let me not make it d, let me make it r. No, let me make it d. And the was it the diameter or was it the radius? Diameter was 50 centimeter, that means radius was 25 centimeter. And then you have pi r square, and this is the radius of telescope mirror, and d is the distance between telescope and bulb. Okay, and this ratio you have been given essentially. Okay, so let me just cancel out the pi, then so it's 2d by r square, and this ratio you have been given as now you just need to know the d is much bigger than r, so it's going to be 60 divided by all of this monstrosity. What is this? 10 raised to minus 5, so it's 10 to the power 6. That is what you have been given, and that's equal to 60 by 0.00006 watt divided by watt. Do you understand why this is the case? It's not like I can hear you. Let me see if I have made it clearly and understandable. It's you don't have to worry about how the energy is produced. You just know that the energy that you receive is the function of the area of the total area that the energy is like spanning, and your total area is pi r square, where r is the radius of your mirror, and the total spherical area that the energy spanning is 4 pi d square, where the d is the distance between you and it. As the radiation extends outwards, it just gets bigger and bigger, that sphere, because light has a speed it travels anyway. And we know this r to be 25 centimeter, which is like 1 by 4 meters. And that square, will cancel this square and make it 10 cube instead. So 2d is uh, 1 kilometer into 1 by 4. Is this 2D correct? Because the last time I calculated it, I got it to be 250 meters, which is so D is 125. If you got another answer, please let me know because I might have made a mistake. I mean, I can't do that. So don't never take my answer to be the right answer. The right answer is what you calculate. Well, you could also be wrong, but then if like more people suggest it, then I can look into my answers and check for errors. But you could also know that I'm definitely wrong. And anyway, so this is how far the bulb is, and you can see that just in that much, just 125 meters, the 60 watt is reduced to 0.00006 watts on a 50 centimeter diameter mirror. This is the symbol for diameter. Okay, so I hope this is understood. Why do I do this when I have a ruler here? Sometimes just hard to say ruler, I swear. Okay, the next question. Now this is the last question. Oh, this is question 3. No, it's question 4. Now let us attempt question 5. Jupiter's apparent magnitude is 2.0 minus 2.0. Let us confirm that. I mean, it depends how close it is to us and everything. Now, right now it's minus 2.76, but for simplicity's sake, I have given minus 2. Actually, I'll show you how it changes throughout the year. Now, press space to center on it and then remove Earth, otherwise it just dances around. And you have to fast forward, but you have to do it in the right. This is not a right. Okay, and let me remove cardinal points. Now time is going, okay, not so quickly. Now we are actually going around the sun, if you can notice. And okay, look at it. 2, that's the least actually, and the highest is like, oh, minus 1.9, and at one point. Oh, it even went to minus 1.8. That's dim. And at max, it's like 2.5. 2.76 is like right now, I don't know. Okay, anyway, this is a cool animation because you can see how you go around the sun actually. If you let me just make it slower to catch the sun. Oh, okay, if you center it around the sun, then you can like, visualize how it is happening. See, Mercury is going around the sun in a spherical manner. And imagine how difficult it must have been for the ancient astronomers to imagine that the planets are going around the sun. Not ancient, modern astronomers. Before we all thought that they were going around each other, around us. Anyway, um, you can actually visualize that the earth is going around this sun as the year is passing, and this is one of the mind-blowing animations that you can think of. And you can also, you realize that the plane is changing. It's because our axis is tilted. That's why we have seasons. Okay, anyway, Jupiter's magnitude 2. What would be the apparent magnitude be if he were, I say he because I am just like, English doesn't have genders, but then German has it, Hindi has it, Marathi has it, Russian has it. So English in my head is a minority language, as in it forms minority, that a language that doesn't have genders. The rest of all the other languages have genders for. So guru is he, even like guru is supposed to be, Jupiter is supposed to be a guy, like it's Zeus, so he were twice as far away. Now this you can do. I'm just not gonna tell you because it's like maybe you can't do it. Okay, so if we were twice as far away, then the intensity would be 4 times as dim, and you need to find out how many. So you need to basically find out 1 by 100, or I don't like 1 by 100 raised to 1 by 5 raised to what number equals 4? This is like 2.5 raised to what is 4? And that's the difference that you need to. So if this x comes out to be, let us say, 1.4 or something, then that means that Jupiter would be -2. This side 1.4, so it would be like minus 0.6. But that's not the answer, but I'm just telling you how it's gonna come out. Please do it, and you can either comment, but if you comment then the others will see it, so don't comment it. You can PM me and I'll soon figure out a way to submit answers. Okay, so what is the x? And what would be the apparent magnitude if the radius were half as much? Now, Jupiter is not a radiative body, it reflects, so the surface area of it is, you will figure it out. Actually, it's not that difficult. So if the radius were half as much, then the surface area is 4 times smaller. It's the same thing, right? Is it? It is. It is the same thing. It's the same thing as being twice as far away. Or is it? I think so. I definitely think so. Because half as small is the same as being twice as far away. Yes. Why not? Yes, when you say half as small, you mean radius and not surface area. Then it would be problematic. So yeah, please solve this. I'll stop streaming and I hope that the quality was good enough. End stream.